Hello everyone. In the last lecture we have completed almost the discussion of passive integrated optical components, which includes power splitters to Mach Zehnder interferometers, ring resonator, distributed Bragg reflectors, etc. So those are we consider as a passive device because as you fabricate you don't need any external control to change its performance. As designed, as fabricated, you want to use them for different type of functionalities and also for integration of large scale integrated circuits. Now today I want to start a new chapter that is actually tunable devices and of course reconfigurable circuits. So sometimes a device which is designed and it's fabricated and the performance also passive performance you want to use, but occasionally or whenever needed you may want to reconfigure or you may want to detune its performance from one particular operating wavelength to another operating wavelength, for one particular functionalities to another different type of functionalities. All those type of things you can actually program, you can reconfigure. So those type of circuits are very much important. Sometimes we call them as active devices or actively configured or reconfigurable circuits. Before going into the details, I would like to give you some information about phase error interference. So when you fabricate a device, fabrication has its own challenge, own limitations. It may not happen that whatever you design after fabrication, the device parameter, design parameters is not coming properly, okay? Or maybe for large scale integrated circuit, wafer scale integration whenever you are doing, in that case one particular location of the wafer, it can have different type of fabrication tolerances because of the dimensional error, because of the process related errors, and if you compare with another location, because in a foundry, in an industry, when you fabricate integrated circuits, CMOS compatible integrated photonic circuits, you are fabricating in wafer scale, 200 millimeter, 300 millimeter diameter of wafer, entire wafer you will be fabricating. So similar type of dies or devices you will have in different locations, but because of the process errors and maybe wafer related errors can cause some kind of dimensional error in your device, fabricated devices. So, so those type of errors, how to correct? How to get uniform yield of all devices, all circuits across the wafer, or a certain wafer, certain device, you wanted certain performance, but after fabrication you see because of the deviations of the dimensions and at different locations, the performance may be different. So that difference of performance is mainly because of the we call it as a due to the phase error, because all integrated optical devices, photonic integrated circuits, everything, if you consider the performance, the functions actually heavily dependent on interfering different waves coming out of different waveguides. For example, if you want to have a Y junction where two waves, two mode, guided mode can come together and can combine and they can interfere, and depending on their phase relationship you can see what is the output intensity or power there itself. So phase plays an important role, very important role. So that's why if some phase error comes because of the fabrication defects, fabrication related process errors, that phase error actually interfere your device performance. That's why we just give this subtitle as a phase error interference. So I would like to give you an idea, some ideas, with examples that how precise phase control is needed for any passive waveguide devices to have some kind of desired performance. Okay, after that I will explain that what I meant, that the different process errors, different fabrication, different wafer level dimensional error, etc., they can cause this type of phase error or dimensional error. So, I will just touch upon some of the sources, various sources of phase errors, and for those phase errors what would be the consequences in device performance. These two things I will be covering in this lecture today. So, let us take an example of Mach-Zehnder interferometer. We have explained this before. It is just a simple Mach-Zehnder interferometer. It is one input is here and you are accessing output here, and this is your can be considered as a single mode waveguide. Single mode waveguide. You know, we know that any guided mode that can be defined as some kind of amplitude A and then E naught xy if it is a single mode waveguide, field distribution, and e to the power j omega t minus beta z. If it is an unperturbed waveguide, that electric field can be defined as this one. So, this can be vector, this can be something like that. So, z direction propagation. So, this A I, when I consider, that is the amplitude of the incoming field of the guided mode that represents. And then in the Y junction we know that amplitude splitting happens, and following the energy conservation you will have A I over root 2 in the upper branch, A I over root 2 in the lower branch, if these waveguides are symmetrically splitted through Y junctions. And this field, again the amplitude reduced, identical waveguide, this waveguide looks identical and this is also identical, waveguide comes here and then it goes through here, and you assume that there is a phi phase difference happening in the phase introduction, additional phase introduction in the upper arm compared to the lower arm. How that can happen? Suppose this length L1 and this length L2, suppose L1 not equal to L2, okay, then additional phase difference between these two arms you can have. Even you can consider that this waveguide width, for example here it is W2 and this is actually W1, and if suppose this W1 not equal to W2, you can consider that L1 equal to L2 but W1 not equal to W2, then also you can say depending on the waveguide dimension, etc., this phase comes. And different regions I will discuss that what could be the regions. If there is a phase errors is there in the upper arm phi for example, then we can say that at the output this comes with A I by root 2 along with whatever the propagation phase e to the power, say total length, if it is this one I can consider this one is L, if L1 equal to L2 you are just considering L, and then along with that e to the power minus j beta L you have e to the power j phi air phase will be introduced. Now at the output if you just calculate the output amplitude by superposition of this field from the upper arm and this field from the lower arm. So, we just according to the superposition principle, again the transfer function gives you 1 by root 2 factor. So, this one will be this part, it is coming from lower arm and this one coming from upper arm, and if you do just A naught star, we can just, this would be proportional to your P output, power output. So, you can say that it's a power output can be defined by Pi. Pi is nothing but Pi we can consider as AI star. All these we have discussed earlier. So, like this. So, if you see if phi equal to 0, then what happens? 1 cos 0 equal to 1. So, P out will be Pi. So, if there is no phase difference between these two arms, then you are supposed to get whatever you are launching here power, same power you will be getting here. This is suppose Pi, this is suppose P naught, and this you are getting at the output. That is simple. And assumed that there is no loss in the entire structure, waveguide losses etc. we just ignore here. If some losses is there, so you have to consider maybe if it is total length is something L, then you can consider P out will be Pi e to the power minus alpha L and so on. Alpha is the power extinction coefficient, power loss coefficient. And you see this can be a little bit simplified in terms of single term instead of 2, you can write cos phi equal to cos square phi by 2 minus sin square phi by 2, 1 minus sin square again cos square. So, it will be 2. So, it will be getting these values, power output. Now, we are talking about phi, this phi, where from it can comes. So, phi we can consider total phase in the upper arm. Suppose effective index in the upper arm we consider as a n effective 1, that is what this one, okay, and lower arm n effective 2. This is not square, this is just this 2 is just for waveguide 2, that means lower arm we are considering. Upper arm length is L1, lower arm length is L2. So, upper arm total phase will be 2 pi over lambda times n effective in the upper arm times L1, that is the phase acquired in the upper arm in the Mach Zehnder interferometer, that is actually we are calling as a phi 1. And similarly 2 pi by lambda n effective 2 effective, if they are not identical waveguide I mean to say, and length is also not identical, that will be phi 2. Of course, we are considering lambda is the operating wavelength, that is same for both the arms, because same wave you are splitting into 2 arms, right. So, this would be your phase. So, for example, if you see somehow if this pi is actually instead of 0 it is pi for example, then 1 minus 1, that means P out will be 0. So, everything will be lost then. So, that is what you do not want. You want something, a certain phase to be introduced here, and accordingly certain power you should be getting at the output. So, similarly, if I just think about another example of a directional coupler based power splitters. So, as we saw before that a phase errors can actually deviate the output power in the Mach Zehnder interferometer, because it relies on interference between two waves, and these two waves, if slightest variations of phase is there, that will be reflected in your output. Here also if we just consider a directional coupler, which we have discussed earlier as well, you just consider the amplitude of the incoming wave coming through this waveguide A naught. Of course, again power we consider here in this case input power may be A naught star, a little bit difference here. I just put input power as A naught here. And after it interacting length of L of a directional coupler, two waveguides, they can be identical, they can be non-identical. So, these two waveguides can be different also, different dimensions, different propagation constant can be, and they can come closer, maintain parallel distance if you want. Then in this region, that is the interacting length basically. As they propagate, it will see the presence of the second waveguide. Similar thing also happens if you are launching here, it will see the presence of the first waveguide. So, we are just giving example of just launching at the one of the input ports in the upper arm, and then you see some field you will get here in the A1 at the so called we call it as a bar port. This is your bar port and this is your cross port, because this is crossing here, that is why cross port. So, A1, that means after interaction of length L, whatever survives here, that will be going here, and whatever leaked tunnel to the second waveguide, that will be coming here. So, whatever survive, that expression we have actually given earlier using coupled mode theory. Okay, this is the expression e to the power j delta L cos SL minus j delta by S sin SL A naught. A naught is the input, that is our amplitude, and where we know that we define the phase actually here in this case, this delta times L, that we are just considering as a phase delta phi, so differential phase we are considering. Okay. So, that is nothing but actually beta A minus beta E. So, this one propagation constant, if we are just considering beta A, this is beta B we are considering, right. So, beta A equal to 2 pi over lambda n effective A, that means effective single mode waveguide, but effective index can be different depending on the dimension, and waveguide B, that means lower waveguide 2 pi by lambda n effective, if there is a difference is there. I think this we have solved earlier. Normally, you know, this delta we have just defined as 2 delta we have defined as, you can recollect from the coupled mode theory, that beta A plus kappa AA minus beta B plus kappa BB. So, that means this is the term kappa AA is considered that modification of propagation constant in waveguide A because of the presence of second waveguide, that is what we call as kappa AA, that is modification of propagation constant. And here modification of propagation constant in the second waveguide beta B propagation constant because of the presence of the first waveguide, that is why we call it kappa BB. So, if you can just approximate kappa AA equal to kappa BB, they cannot be they may not be equal, but if we consider that one, then simply we can write beta A minus beta B by 2, 2 is there. That is what we have used in the coupled mode theory. Accordingly, we have derived this, whatever the amplitude you expect in the bar port and in the cross port. So, in this fashion, if we just define delta A equal to delta phi, that will be like this, where this S also we have defined kappa square delta square. This kappa is actually we call it kappa AB, and that we consider as a kappa BA, for example, that is actually kappa A. That means how much coupling strength, whatever per unit length, whatever coupling because of the perturbation or because of the presence of the second waveguide, that all these we have discussed earlier. I am not repeating, just expression I am just introducing here. Now, if you see another way we looked into it, and we have shown also that you can think of super mode excitation, symmetric mode with a propagation constant beta S and asymmetric mode with a propagation constant beta S, that is the solution coming out of combined structure. And then beta S can be written as, if operating wavelength is lambda, so n effective S. So, symmetric mode, what is the effective index, and then 2 pi by lambda times n effective AS. Okay. So, we can show that this kappa can be expressed, if you know this n effective S and n effective AS, then we can show that this kappa, whatever kappa we are considering, kappa AB, kappa BA, that can be expressed as kappa equal to pi delta n by lambda, where delta n equal to n effective S, n effective AS. They are the solution of the super modes, eigenmode solution of the combined structure and corresponding effective index. So, that means we know that this delta phi actually involves delta, okay, and that actually contributes how much amplitude will be coming here and how much amplitude will be coming here depending on S value, kappa value and delta square value. So, ultimately we see, you have to see that n effective A, n effective B, or n effective S, n effective AS. When I talk about n effective A, that means effective index of the guided mode in the waveguide in the absence of first waveguide, in the absence of the second waveguide. Similarly, n effective B is the effective index of the guided mode of the second waveguide in the absence of the first waveguide. But when we talk about symmetric and asymmetric super modes, then we can solve combined structure. Then individually, if they are guiding single mode, collective combined structure that can have two modes, we call them as a super modes, and those super modes will have effective index, so called n effective S, we can define like that, and n effective AS. So, in this way we can find kappa value from there, and this kappa value can be used here for S, and delta value can be expressed in terms of beta A and beta B, and then we can find out what is the amplitude here, what is the amplitude here. So, suppose delta equal to 0, this would become just like a cos. If delta equal to 0, this would be coming like a cos kappa L, and this would be coming like a delta 0, this will come like a minus j sin kappa L A naught, of course A naught here. So, this will be cos value, this will be the value delta equal to 0. If in any case delta has some non-zero value, out of the variation of n effective A or n effective B, then this variation can cause the output power different than what you desire. So, these are actually it is coming, all this effective index changes, differences, etc., that actually introduce as a phase. So, that means this phase error, actual phase has to be precisely controlled. If you want a delta, specific delta, that delta should be there. Because of the fabrication error, it should not differ, so that whatever you desire you are not getting, for example. So, this precise control again needed for directional operation if you want to use it as a passive device. Now, third important component, and so I would say that the most important component for photonic integrated circuit, called micro ring resonator, sometimes you call it as a MRR. As you know, in a micro ring resonator, it is given as a all pass configuration. All pass configuration, where you have a ring and one bus waveguide interacting, where light will be tunneled here bit and round trip pass again comes back. In steady state, you know that how to solve the transfer function and what would be the B naught, and we can find out the transfer function T can be B naught by A Bi square. That will be the power transfer function, we know that. In the power transfer function also, we have shown that the resonance condition should be, that is called phi cavity, round trip phase. Because of this round trip travel, beta L, beta is the propagation constant of the waveguide, that must satisfy 2 pi times integer. Then that beta value gives you corresponding lambda, beta equal to 2 pi by lambda n effective is resonant in the ring, and that can store. The field will be enhanced and that particular lambda will be missing in the output. And you know that in a ring resonator, as a function of lambda, if you see in the transmission T, you can normalize transmission 1, then you see that repeatedly, periodically some wavelength that should be same width, some wavelength will be missing in the transmission. That means that lost energy will be stored in the ring. That is how you get a certain wavelength range. If you see, this would be like a notch filter. Okay, m is the integer, it can start from, obviously it should not be 0. If m equal to 0, round trip phase cannot be 0, so 0 need not be considered, it can start from 1 and so on. And then this phi cavity, we can say that 2 pi by lambda n effective L. Again, if you see, if there is any error in n effective compared to your desired design, then you can see that you may not get a desired wavelength of resonance. I will explain more details in next couple of slides later. Now, the fourth important device we have discussed so far is the distributed Bragg reflector. We call it as a DBR. Okay. You see, we have discussed very recently that periodic perturbation is there, rectangular perturbation you are launching here, then you have forward propagating wave and backward propagating wave will be generated, and that backward propagating wave will be grown, will be enhanced if you maintain a certain condition, so called phase matching condition. You remember that phase matching condition, if it is a single mode waveguide, that phase matching condition or that delta beta we define by delta beta, that is actually AM over 2 pi by lambda. That is the phase matching phase mismatch. So, if delta beta equal to 0, then it is called longitudinal phase matching condition. In that case, 2 beta equal to m 2 pi over lambda. Lambda is the periodicity, right. So, now if you see that you can consider 2 beta lambda equal to 2 m pi, that is what I have written as a phi b, that is actually we are writing as a phi b. So, this is required, phi b called Bragg phase, phi b, if this matched the corresponding 2 pi by lambda n effective, that particular lambda will be reflected back, called lambda b, Bragg wavelength. Okay. So, we write this one again a little bit modified one, 2 times beta means 2 pi by lambda n effective and then lambda, that is your phi b. Again you see, you have to have, if you want to have this lambda as a lambda b Bragg wavelength to be reflected, this phi b has to be matched. This phase condition, this type of phase is needed. At any cost, your N effective is differing because of the dimensional error, fabrication error, etc. coming due to your process related error, I mean to say. Then you can say that, okay, that lambda b, desired lambda b Bragg reflection you won't be able to see. Okay. Similarly, again we saw Fabry-Pérot cavity, Bragg reflection, this is a Fabry-Pérot cavity, using that also we have discussed Fabry-Pérot cavity. DBR1, DBR2, reflection spectrum R1, reflection spectrum R2, right, and length is L. Then we know that if you want to see a resonance within the, suppose Bragg 1 is giving this type of reflection and Bragg 2 is giving this type of reflection, then both sides you get a positive feedback, then you can see, depending on the round trip phase condition, you can see some kind of longitudinal modes within the Bragg response. And in that case, you see longitudinal mode resonances, that we need the 5 FP Fabry-Pérot, that means whatever round trip propagation, whatever the phase is there, and phi 1 may be introduced by the Bragg wave DBR1 and phase 2 introduced by the Bragg DBR2, that should be 2m pi, we have discussed earlier, m equal to 0, 1, 2, 3, that also discussed integer. So, this is the condition for longitudinal mode resonances. Now again, phi FP, if we are just considering, let us consider that phi 1 and phi 2, whatever comes, we know phi 1 and phi 2, they can give some kind of phase difference. As you know, DBR can introduce some phase exactly at Bragg wavelength, that is pi by 2 and so on. And if you just simply that is somehow defined with your DBR, that phase also can control, there is any variation in this phase because of the dimensional error, etc., you may get a different resonance wavelength. Similarly, only if you just consider Fabry-Pérot just phi FP, that means 2 beta L, phi FP will be 2 beta L. If L is the this one length, then 2L is the round trip length, and round trip propagation constant multiplied by round trip length, that will be the phi FP. That Fabry-Pérot related phase we are considering, that must be equal to 2 beta L, beta equal to 2 pi by lambda N effective, L is multiplied. Again you see N effective comes here. So, if there is any error in effective index, that error can come because of the again fabrications or any other influences, that will cause variation in phi FP, and then phi FP variation will actually derail your resonance wavelength, detune your resonance wavelength, which may not be desired for you. Okay. So, we have given 4 examples, say Mach Zehnder interferometer, directional coupler, and then micro ring resonator, and then DBR. So, 4 different important devices we have discussed, where we have found that the precise control of phase is required to have certain kind of output function. If it deviates, then your operating wavelength to resonance wavelength to everything will be changed, and that will be a catastrophe. Okay. This is actually important part. Phase control is very, very important. Now I will try to give you some quantitative value, that how this N effective can vary because of the fabrication related, technology related, process related error is there in terms of dimension and etc. of the device. Okay. Let us see a waveguide. Let us consider a waveguide, silicon on insulator waveguide. And silicon on insulator waveguide, you know, one type of this is your box layer, and then device layer is structured like a rectangular things. In the top, maybe top oxide layer is there, and this is some kind of photonic wire waveguide structure. It will have a dimension like W and H. But if you have a rib type waveguide structure like this, then you can have a waveguide parameters that will be W, H and small h. So, according to your design, suppose you wanted certain waveguide width, certain height I have, and certain slab height I want. That particular parameter, that should be maintained throughout the waveguide. Anywhere, any place, any deviation of WH small h result into a deviation in your mode solutions, or in another word, deviation in your effective index calculations. So, as we saw that effective index variations can cause a lot of problem in your integrated optical device performance, right. That is, precise control of an effective is very important to have a certain resonance wavelength, certain performance power output, and so on. So, here we try to show that if you just consider a waveguide length, suppose this length is about L, and if it is perfectly designed, pure according to your design, and it is uniform, I mean pure means I mean to say that uniform throughout the waveguide length, then it will have a beta propagation constant, and for a length L travelling, whatever the phase, this is phi equal to beta L. If I just say operating wavelength is lambda, 2 pi by lambda and effective L, that is fine. Now, if I see that if this phase is slightly varying, deviates, differential change happening, and what are the reason? Either lambda should vary, or ineffective should vary, or L should vary. These three different parameters you have to think about. Okay. So, if I just do so, that what causes differential change of delta phi? So, you just make a differentiation, then you can get first term, you can do 2 pi by lambda square minus value delta lambda n effective L, that is what the things I just differentiate with respect to for lambda, and then if we differentiate, then any differential change for n effective 2 pi by lambda constant, L constant, delta n. Similarly, if variation length is varied, 2 pi by lambda n effective delta L. So, this little bit modify this one, you just take a factor of 2 pi by lambda n effective L from all the three terms. Then what we will be getting? First term will be this is delta n effective by n effective, delta L by L, minus delta, this is the minus delta lambda by lambda you will be getting, right. So, this is as usual, this actually whatever you get, supposed to get your beta value, and if you have any deviations in n effective or delta L or delta lambda, then your delta phi change will be calculated accordingly. Fine. So, let us assume for our general discussion this delta L is 0. That means length variation is not happening, because you wanted a certain length of waveguide device, you can fabricate that more or less accurately. And suppose your operating wavelength is fixed lambda, so that means delta lambda also will be 0. So, delta L 0 and delta lambda equal to 0, we can just assure that. So, if we do so, then delta phi only changes delta n effective. That is what repeatedly I am saying, that any phase variations, its most important culprit is that any ineffective change, effective index change, delta n effective change. Delta L length we are just assuming not so critical. Okay. So, that means delta n effective change can cause your phase deviations. That phase deviation in turn cause your device performance, because all the devices, photonic integrated device, they rely on interference. Interference need certain phase relationship to have certain kind of interference. Okay. Now, let us see what causes this ineffective change because of the fabrication error, process related error. Okay. So, you have waveguide width, you have waveguide height, and you have your slab height h also. This is your slab height, right. Slab height is there, and if it is a photonic wire waveguide structure, when slab height slab height small h 0, then it is kind of rectangular waveguide structure that we have earlier we have discussed. So, dimensional related, the n effective, if you see n effective, if you just think of that n effective must be a function of waveguide width, how much you are designing, waveguide height, how much you are designing, slab height, of course this slab, how much device layer you are leaving here for defining your waveguide, and of course temperature of the device sample. So, n effective, because silicon is a very good thermoptic material, and you can say that for a raised delta T amount of temperature is increased, then we can say that the delta n change in the bulk silicon, if you are just considering, that will be something how much it is changing per degree Kelvin or centigrade, and then what is the amount of temperature you are changing. So, for the bulk silicon, this value is not N effective, I should not say N effective, it is bulk, then it is delta N silicon for example. So, for delta N silicon that is called temperature coefficient, that is actually about 1.86 into 10 to the minus 4. It looks very refractive index change per Kelvin, that is per Kelvin. Okay. 1 Kelvin temperature change cause this much refractive index change. It's simple, it is looking very small, 10 to the minus 4 order, wherever if you see silicon bulk is about 3.477 something like that, 776, this type of refractive index at lambda equal to 1550 nanometer wavelength. With respect to this one, you can have 10 to the minus 4 change if a temperature fluctuation of 1. So, that means if bulk refractive index change is happening instead of ND, you are just varying, it is not constant over temperature, then you can say that this effective index also temperature dependent. So, we are just on the top of it, you can consider if it is a bare structure like this top oxide layer is not there, it is just open, then you can think of that it is exposed to the air, and air also you can have some kind of in the open ambience, it can have certain kind of humidity. So, humidity can change over time, and depending on the humidity, surface layer air, normally in air we consider refractive index is 1, but if humidity changes also you can see that refractive index change can be in the order of minus 10 to the minus 4 or so. So, those type of humidity everything can also play a major role. However, when you have a silicon TOX layer or silicon dioxide top layer, TOX, so called TOX we are considering, in that case you do not get really your device is not really directly exposed to your ambience humidity, so we can ignore that. So, in turn what I mean to say that your effective refractive index of the guided mode that can vary if you are varying W, if you are varying capital H, if you are giving H, because all this thing calculation of effective index in your mode solver or when you solve the guided mode etc., they are basically all this parameter we have shown that they can change the refractive index. So, mathematically if we just look into it, just see how much differential refractive index change can happen because of different parameter variations. So, we can just define this one. That means this is one type of coefficient per unit change in waveguide width, how much refractive index change can happen, effective index change can happen for the guided mode. Similarly, per unit change of the device layer thickness, how much effective index can change, because if you have a wafer like a 300 millimeter diameter, like this 300 millimeter diameter for example 30 centimeter, or it can be 12 inch 1 feet diameter, and you know that if you see it, it is a 3-layer system. You have a substrate mostly 500 micrometer to 500 micrometer to 700 micrometer, then you have a box layer about 2 to 3 micrometer, and then a device layer that is about 220 nanometer, 300 nanometer and so on. This is your SOI layer. So, 3 layer, and this device layer is supposed to be 220 nanometer for example, but if you see when it is you are buying a SOI wafer of 300 millimeter, this they will say that it is everywhere may not be 220 nanometer, there may be some variation of plus minus 5 nanometer and so on, thickness is there. So, capital H thickness is there if you are defining a certain waveguide with certain width, thinking that it is 220 nanometer, but actually your device layer thickness is more than that or less than that. So, you can also think a considerable contribution of this device layer thickness variation. So, del N effective del H, if it is some variation is there, then we can find that. And similarly for small h, slab height and temperature. Okay. So, these 4 parameters we need to know. Suppose I want to operate I design a waveguide W equal to 500 nanometer. I want to design with a device layer thickness equal to 220 nanometer. I want to have a device layer thickness of, for example, 150 nanometer. And I want to have a temperature, operating temperature maybe around 300 Kelvin, room temperature, 27 degree or centigrade or 300 Kelvin. Somehow, if your width varying somehow plus minus something, this varying plus minus something, and that is coming from your process related error, and temperature may be fluctuating maybe 1 degree while operation or something like that. So, what could happen? So, we have estimated, simulated for a REEB waveguide of W equal to this one 220, H equal to 100, consider plus minus 10 nanometer variation can happen in slab thickness, plus minus 20. This is just a wild example. It may today you can get much lower values, of course, variations. Device layer thickness 220 nanometer plus minus 220 nanometer, and whenever you are defining your waveguide in photolithography or e-beam lithography or advanced lithography system, then you can think of that waveguide dimension can vary plus minus 20 nanometer. It's a probabilistically it can vary. Maybe one wafer location to another wafer location, it can be different. And we have seen that if we just around 500 nanometer, it's 20, small is 150 nanometer. If you see, if slightest variation per unit length, per nanometer waveguide width, you just think about 500 nanometer, if it is 501 or 500 minus 1, then you can see that 10 to the minus 4 refractive index change can happen. Similarly, height, thickness, device layer thickness 1 nanometer variation around 220 nanometer. So, you can expect a refractive index change of 2.1 times 10 to the minus 3. Similarly, del N effective by del H, if you see refractive index variation of 10 to the minus 3, you can see. Okay. So, basically this device height, device layer thickness which is lower, slab height which is lower, their variation can cause you actually higher refractive index change compared to width sensitivity. As I say that if you are considering waveguide, temperature variation, our calculation shows that it is in the order of 1.7 into 10 to the minus 4 per Kelvin. This is the coefficients, refractive index coefficient with respect to width variation, with respect to height variation, with respect to slab height variation, with respect to temperature variations. Okay. Now, if you just consider instead of slab waveguide, you can consider this type of waveguide where H is equal to 0. So, in that case, again you consider W equal to 500 plus minus 20 nanometer, H equal to 220 nanometer and so on. Small h variation, you do not have a small h. So, here also you see almost del N effective by del W in this case relatively higher. It is instead of 10 to the power minus 4, you are getting about 10 to the minus 3, because width now, because you do not have this bulk actually contributes a lot for temperature stabilization, etc. If it is not there, actual temperature stabilization, width variation, sensitivity, etc., all those things can happen. And height variation won't change much, so maybe 1.5 times or so compared to waveguide structure, and for temperature variation it is almost same we can consider. So, that means your fabrication has to be really a high tech, really a nanotechnology required. But you can always ask question, when your refractive index changes in the order of 10 to the minus 4 and 10 to the minus 3, what is the big deal? I will show you that this is really a big deal. Even if it is 10 to the minus 4, 10 to the minus 3, that is a big deal, big problem for your device performance. So, I mean to say that even 1 nanometer variation in width, height or slab height variation, that cause a huge problem in your device performance. So, that means you have to be that much careful that your device should not deviate even 1 nanometer, 2 nanometer in width wise and height wise or so on, if you want them to use as a passive devices, of course. Okay. So, that is very important conclusion. So, I would like to show that, okay, does it matter that 10 to the power minus 3, minus 2, 10 to the minus 4 variations really matters. Let us see example of again our Mach Zehnder interferometer. We have shown that phi equal to this one we have expressed. Let us consider that operating wavelength is 1550 nanometer, and we consider this L1 and L2, they are identical, balanced Mach generator interferometer 100 micrometer. However, because of the dimensional variation, for example, N effective 1 and N effective 2, I have just a little bit exaggerated. Instead of 10 to the minus 3, we just consider 10 to the minus 2, for example. Okay, 10 to the minus 3 you can consider, but it all depends on again length also. If you just consider delta n variation between these two arms is 10 to the minus 2, then if you calculate phi, that is actually coming 1.3 pi. That means wave propagating here and wave propagating here, they will see their phase difference is about 1.3 pi. You know, pi difference can cause complete disappearing in the output. Everything will be lost in the junction. But it is 1.3 pi, little more than that. So if you calculate what is the power, you just put 1.3 pi here, you get only 35% output here. 65% will be lost. So 10 to the minus 2, if it is there, you can have 10 to the minus 3, and suppose you are considering L equal to 1000 micrometer. Same effect. Refractive index variations, difference in refractive index if it is 10 to the minus 3, and if you are using 1000 micrometer here length, that they are also, you see, 35% of power will be released. That means just 1 nanometer variation in device layer thickness or 1 nanometer variation in device layer width, you can have a huge problem. You were ending up with a 35% output power instead of 100%. Take another example, a ring resonator. We have shown that ring resonator cavity, this is the resonance condition, we have discussed again and again, and this if you just this you concentrate here, that beta equal to 2 pi by lambda m, I have written that is the resonant wavelength, mth order resonant wavelength, just to respect m here. N effective is the guided mode effective index, L is the round trip length of the ring resonator, this is total length is L, perimeter length. So this one, so this equation can be modified to this one, and if you just simplify the 2 pi cancel, then you can say that N effective L equal to m times lambda m. Okay. So m we put 1000, for example 1000 order of longitudinal mode order, and you know N effective is about, let us consider N effective say 2.8, L equal to 100 micrometer for example. Then 1000 times lambda m, whatever you will be calculating, that will be in the micrometer, because this is micrometer. So lambda m will be 2.8 times 1000 times 100 divided by 100 micrometer, right? So 100 cancel, so that will be 2.8 micrometer. I am considering, if you are considering 1000. If it is 1550 nanometer, the mth order will be lower, right? Little bit modification here. Let us see any differential change in effective index. So I differentiate L, I am just considering maybe constant, perimeter is constant, nothing happening to length, that is according to the design coming. Only dimensional error, cross sectional error, W, H, small h, this error is there. Delta N effective L, that means m is fixed, same order of resonance wavelength I am considering, delta lambda m. So your wavelength same order, but resonance wavelength will be varying delta lambda m. So from here I am just writing here. So delta N effective times L equal to m, again I can write m is equal to N effective L by m, L lambda m. So N effective L by lambda m, instead of m, N effective L by lambda m I am considering, and delta lambda we are writing. So this is simply m I replaced. And then if you just compare these two thing, L cancel, I can consider delta N effective by N effective equal to delta lambda by lambda m. So delta lambda m by delta lambda m is this one. So that means slight differential change in your effective index or dimensional error, then you can find out how much shift can happen in a resonance shift can happen in a ring resonator. Okay. So in that case, what we do, let us assume I am expecting a resonant lambda m, say particular resonance as lambda r, 1550 nanometer, and N effective we can consider about 2.8 of a fundamental mode, single mode waveguide 2.8. And suppose your delta n effective change happening because of the dimensional error is 10 to the minus 2. If you just calculate delta lambda m will be delta lambda r, that means resonance detuning will happen 5.5 nanometer. So 5.5 nanometer resonance detuning is a huge. Suppose you want to operate at 1550 nanometer resonance, now it is giving you resonance at 1550 plus 5.5 nanometer. You know, I2 channels for communication, etc. If it is 200 gigahertz I2 channel, that means it is about 1.6 nanometer. It is 5.5 nanometer spacing, 1.6 nanometer spacing of I2 channels for DWDM communication, and you are getting 5.5. So that means 3 channels will be hopping. So that's a huge problem. 5.5 nanometer resonance detuning just because of the 10 to the minus 2 refractive index change. If it is 10 to the minus 3 refractive index change, this would have been 0.55 nanometer. That is a lot also. That is also very much sensitive. So that means 1 nanometer waveguide width variation can cause your resonance shift a lot. Half a nanometer shift can happen also. Okay, particularly for high Q ring resonator, this half a nanometer shift means you are gone completely outside of your resonance wavelength. So that's a huge problem. Okay, now last thing is that if slightest change in the DBR structure, distributed reflector DBR, we have discussed earlier. Here also the Bragg reflection happens. We discussed that this condition has to be fulfilled, 2 beta times lambda. That means if it is a period, this is your period, for example, we are just considering this to this period, that is your lambda. That means round trip phase in every unit cell, round trip phase, that is beta times 2 lambda, should be m times integer multiple of 2 pi. So this one can be expressed as 2 pi by lambda b if it is a Bragg wavelength. Of course, this is a Bragg phase we defined earlier, n effective times lambda, then this should be equal to this one. So ultimately you get this is the Bragg wavelength we can calculate. If we know the period, if we know the n effective, and if we know the grating order diffraction, mostly it is 1, then we know lambda b equal to 2 n effective lambda. So this is the grating order, which order, diffraction order you are using for your Bragg phase matching condition, that we have discussed earlier. You can just see back. Now if you do this one, a differential, you just differentiate both sides, then what you see, 2 delta n effective lambda, 2 n effective keep constant, period variation if you are just considering any variation happens in the period, delta lambda, m is the grating order we are considering same, m delta lambda b. So delta lambda b is the deviations for the Bragg wavelength, detuning from the Bragg wavelength because of the variation is delta n effective and delta lambda, right. So if you just little bit manipulate here, then you get delta lambda by lambda b equal to delta n effective by n effective by delta lambda by lambda. You can assume that okay, period variation is this variation, if it is 0, then you can see that this is exactly similar like your resonance wavelength in the ring resonator. So resonance wavelength in the ring resonator, the variation sensitivity, refractive index variation sensitivity is same as the DBR structure Bragg wavelength deviation sensitivity. It is same. Let us assume lambda b equal to 1550 nanometer. Your phase matching wavelength lambda b 1550 nanometer, and effective again you consider 2.8. Delta lambda, suppose it is 0, and 10 to the minus 2 refractive index change can cause again Bragg wavelength detune 5.5 nanometer. You can have a Bragg transmission. In transmission, this one stop band can be say 1 nanometer to 5 nanometer, for example. This is a stop band, say around 1 nanometer, 2 nanometer or 5 nanometer, etc. But what happens if anyway your 10 to the minus 2 change happens, then you get 5.5 nanometer deviation. You will be getting here, somewhere here. Even it is 10 to the minus 3 variations, because 1 nanometer width variation can give you 10 to the minus 3 width, or height variation can give you 10 to the minus 3 refractive index change. So then also you can get 0.5 nanometer variation. Suppose it is 1 nanometer stop band, then it will be just coming somewhere here. Suppose you are operating exactly at this wavelength, that wavelength now it does not see much of the dB response. It will be like a transmitting, like a transparent medium. So that's a huge problem. So it's a really, you need a precise control, precise technology to control that. And so far we know that our CMOS technology, even if it is a nanotechnology, people are using advanced technology up to 10 nanometer technology, etc. But there actually you can go for precise fabrication. But for CMOS compatible silicon photonics technology, we typically use 180 nanometer technology or 90 nanometer technology, CMOS technology node, 45 nanometer technology, these are the latest thing are coming. So far 180 nanometer technology, 90 nanometer technology and 45 nanometer technology. As you go for advanced technology, this type of error will be reduced, no doubt about it. But so far whatever foundry is giving, you have the tolerance, error, fabrication error can happen up to 1 to 5 nanometer variation can happen in width whenever defining photolithographically or using e-beam lithography, something like that. 1 to 5 nanometer deviations can happen in full wafer size. Suppose you have a wafer, you are designing your mask is, suppose you are using to define a waveguide width of 500 nanometer. Here same design would give maybe about 495 nanometer width, but here you can give you 500 nanometer, 505 nanometer, maybe middle you can have 500 nanometer. So entire wafer, if you see different region, waveguide may come out with a different dimensions. And different dimension, 5 nanometer dimension means 5 times into 1.3 and so on, that means about 10 to the minus 2 or so. So that variations can give you this much detuning in DVS structure, ring resonator, Mach-Zehnder interferometer, again pi phase detuning, etc. will happen. So fabrication cannot ensure complete uniform yield throughout the wafer, even though you are using 45 nanometer technology node, CMOS technology node. You can have also the device layer, whenever you are procuring, you are buying the silicon on insulator wafer, as I said that device layer thickness cannot be, you cannot expect device layer thickness throughout 300 millimeter diameter uniform. There will be plus minus 1 nanometer is always obvious, 1 to 5 nanometer. So it's a basically precision nanotechnology required to control all these, and that is so far we do not have. Okay, so it can happen lot of problems. So now if there is a problem, there is solutions, people are coming out with the solution of how to solve all this. We will discuss that in the next lecture, how post fabrication correction of devices. Once you fabricate full wafer, how to correct that if there is any problem in some device performance somewhere, so you can correct that and then you can just use for your different circuit application and packaging, all those type of things can do that. Okay, so I stop here for this lecture today.